We want to find Ixx, its area moment of inertia, about the horizontal axis that passes through its centroid, and Iyy, its area moment of inertia of the axis, the vertical axis that passes through its centroid, or that y prime. Our cross-section is not just a simple rectangle or just a simple triangle, so we will want to use the tabular method in order to calculate both of these quantities. In this case, we have the origin. I'll just use the coordinate system that is provided to us. The origin is in that bottom left corner. And we're given some of these dimensions. This is 2 inches. So what I want to do first, like I did with the centroids, is I want to split this up into multiple shapes, each of which I can easily compute, the first step being its centroid and its area, and then in the second part, easily compute what its area moments of inertia are about their own centroidal axes. So in this case, what options would I have to splitting up this shape into easier shapes? Right, 2 rectangles. Actually, even there's a couple of different options. I could take this outer rectangle and then subtract out this piece or cut out this piece of it. That would be one option. I can split it up into this rectangle and this rectangle, or I could split it up into this whole tall rectangle, ignoring that cut, this tall rectangle, and then this wide rectangle. I would say since all 3 of those methods have 2 shapes, but the first method I'm cutting out a shape, if I can avoid cutting out a shape, I generally would. So I'm going to decide to split it up this way. But we would have just as much success, or it would be just as easy splitting it up into 2 the other way also. But just so we're all on the same page, this is how I'll split it up. Right, so we'll be able to do this in 2 shapes. So the first thing we want to do is start our table, because we need to know relative to the origin, where is the centroid of this composite L-shaped cross-sectional area located. So shape number 1, what's the area of shape number 1?
16.
Right. Shape number 1 should be 16. It's going to be 8 wide by 2. And then the area of shape number 2, 8, because it's only 4 high times 2 is 8. So our total area is 24, and these are in inches squared. That'll be in inches and inches. X tilde for shape 1. Right? The x tilde, remember, is the distance between the y-axis and then the axis that goes through the centroid of that sub-shape. So since it's 8 wide, it'll pass through 4. So 4 is going to be our x tilde. And for shape number 2, our x tilde, right, because its left side is also on the y-axis, half of 2. And for our y tilde for shape number 1, and for shape number 2, we have 2, we have 4 as opinions, although it's not really an opinion. So which is it, 2 or 4? Right, it's 4, right. Remember, we're always measuring it from the same origin. So for this piece, it does have a height of 4 inches. So above its base is going to be 2. But from the x-axis, we have to go up 2 inches and then another 2 inches to get to that horizontal axis that passes through its centroid. So its total is going to be 4. The rest of the table, we just have to multiply across. We get 64, 16, 8, 32. We add down to get 72, add down to get 48. So at this point, we can use that information. All that really matters out of the table is the total AX tilde, AY tilde, and A, so that we can find our X bar and our Y bar value. So our X bar will be 72 over 24, which is 3 inches as measured from the origin. So that means we're 3 inches to the right of the origin. And we have 48 over 24 is 2 inches above the x-axis. So our centroid is located here because it's on 2 inches above the x-axis there. So that's our x prime and our y prime. All right, questions on finding the centroid of our figure? All right, so again, that's not new. What's new, now that we know where the centroid is we can go the next step and find the area moment of inertia of our figure around its x prime and y prime axes. So we add on to our table with those additional rows. We add for each shape its moment of inertia about its own centroid, horizontal and vertical, the dx and dy terms, and then these adx squared and ady squared, and then by adding these together and these together, we'll be able to get our area moment of inertia of the composite shape around its horizontal and vertical axes. So for shape 1, shape 2, we need to find their area moment of inertia around their own horizontal and vertical centroids. That's what the Ixx prime is and the Iyy prime. So for shape 1, what is its Ixx prime going to be? Right, so 5.33. And again, that's coming from shape number 1. We're seeing how hard is it to bend it around its own horizontal centroidal axis. We're going to cube the dimension perpendicular to that, that's the 2 in this case, times 8, and divide that by 12. And we get the 5.33, and then this is in inches to the 4th and inches to the 4th. And for shape number 2, its Ixx prime, again, we're bending around its own horizontal centroidal axis. So we're going to cube the 4 term in this case times the 2 and divide that by 12. So 4 cubed times 2 over 12. For shape 2, we get about 10.7. So it's larger, and we see that shape number 2 is oriented more vertically than shape number 1. So around that x prime axis, shape 2 has more resistance to bending, in at least compared for this Ixx prime. And if we add that together, we get about 16 inches to the 4th. And then for shape number 1, what is its Iyy prime term? Right, we get about 85.3 if I keep 1 decimal. So how hard is it to bend it around the axis that goes around its centroid, just shape number 1's centroid? So we're going to now cube the dimension perpendicular to the vertical axis, which is 8. So we get 8 cubed times 2 over 12, 85.3 inches to the 4th power. And for shape 2, now about that vertical axis, it's going to be the 2 cubed times 4 over 12. And we see we get that smaller value of 2.7. And we add those together, we get 88. So again, to recap, these Ixx primes, Iyy primes, those are just coming from BH cubed over 12 if it's a rectangle, BH cubed over 36 if it's a rectangle, or if it's a different shape. These are always the moment of inertia about the sub-shape's centroid. In the next step, that's where we make this adjustment that our shape's centroid is not the same as the composite shape's centroid. So for example, when I want to find dx for shape number 1, what I'm looking at here is the horizontal centroidal axis through shape number 1 is down here. But through my composite shape, that's the x prime axis, it's up here. So that offset is what I'm calling dy1, the dy value for shape number 1. It's this offset distance. So the dy is, that's the dy, and then the dx is going to be the difference between the sub-shape's vertical axis and then the y prime axis. So that would be, that distance here would be my dx for 1. So my dx I defined as the, sorry, these are actually in reverse. This is the dx and this is the dy. Dx I defined as y tilde minus y bar. So for shape number 1, its y tilde is at 1, that's this, minus y bar at 2. That's how I'm finding this distance from information I already have on the table. And whether you do y tilde minus y bar or y bar minus y tilde, it really doesn't matter. So for this shape, I'm going to do 1 minus 2. I get negative 1, or positive 1. It won't matter because I'm going to be squaring it. For shape 2, I take its y tilde of 4 minus y bar of 2, and I get 2. And then the dy, that's going to be that horizontal offset between the two centroidal axes that I'm comparing. For shape number 1, it's going to be its x tilde minus x bar. I get a 4 minus 3 is going to be a positive 1. And for shape number 2, I get 1 minus 3 is a negative 2. Right, if you put negatives or keep these all positive, either is fine with me, because again, the only thing we do with these is square them in that last step. All right, so again, the tricky part to remember here, the way that I've defined these terms, is that dx was y tilde minus y bar, and dy was x tilde minus x bar. So the dx is defined by y's, the dy is defined by x's. The last step, again, we have all the information we need from our table. The area of our subshape times the dx term of that subshape squared. So a times 1 squared is going to give us 16. We have 8 times 2 squared is going to be 8 times 4, gives us 32. And we get 48 as our total. This is also in inches to the 4th. For shape 1, I have 16 times 1 again is 16. And 8 times 4 again is 32. Yeah.
Why is the dx opposite of what you think with the y?
Because that is the distance between the x-axes. But that distance is a vertical distance. Yeah, so this is the tricky part to remember, these definitions, I think. The last step now for the composite shape, we can take into account the inertias of each subshape around its own centroid, and then we can build in that parallel axis adjustment from what we got on the table. So for the composite shape, I get my total Ixx prime of 16 plus my total ADX squared of 48. So for the composite shape, its Ixx, I get 64 inches to the 4th power. And for Iyy, I take my 88 plus ADY squared. Now, unfortunately, they're both 48 in this instance, but keep in mind that this goes with Ixx and this goes with Iyy. So my Iyy is going to be 136 inches to the 4th.